the model performs very well on the training data, but when we use the model on the test data, we get bad results, we get low accuracies. So when this happens, we have a very high R squared because we have very high accuracy on the training data, but we have low accuracy on the test data. So one of the reasons that can happen is that we have overfitting. So we have too many variables or too complex of a model that actually customizes our model to our data or our training data set. So we are over-customizing our model, we are overfitting our model to the training data set. And therefore, we are not going to be able to generalize the results to other data sets, and the model will not do well on the test data set. The goal is that, so as a rule of thumb, what we should try to do is that we should try to find a model that has as few variables as possible and is as simple as possible, but at the same time can result in as high R squared as possible. So we want to have the highest R squared with the minimum number of variables. That's the goal. So overfitting happens when we have too many variables in the model that will result in high R squared and, of course, high accuracy on the training set, but the performance of the model on any other data is very low. So this can happen with any model. This can happen with the logistic regression, with multiple linear regression, and there are ways to avoid it. So first of all, we should just include the most important variables in the model, the substantial and the variables that make substantial improvements in the R squared. And we should always consider the prediction accuracy on the test data set. And we can use backward stepwise selection to remove the unnecessary variables, extra variables that are not making a lot of contributions to the model. So how can we select the variables? That's actually the big question. So there are different approaches to select the variables, the predictors for the model. One approach is forced entry. So with forced entry, we just select a bunch of variables and we just use them and we run the model, and that's it. We have our model. So it's not very complicated, it's very easy, but you may end up with a very bad model, and our model may be overfitting, it may have a low R squared, etc., etc. So we want to consider different options. We want to consider different potential predictors and see which subset of predictors, which selection of predictors results in a higher R squared and a higher predictive power, while we have the minimum number of predictors, not overfitting. So an extreme approach, an extreme method to deal with it is that we try out all possible subsets of the potential predictors. And we select the model that results in the highest accuracy on the test set. So you know how to find the accuracy on the test set. You just build the model on the training set and estimate the coefficients, and then apply the model on the test set and estimate the errors, and then you can both form the confusion matrix, and you can evaluate the accuracy of the model on the test set. Okay, so we judge the models based on the performance on the test set. So how can we try our subsets? So let me give you an example. Let's say we have 3 potential predictors to predict variable y, predict the dependent variable y. We have 3 potential predictors, x1, x2, and x3. So one subset would be just include all the 3. So the model would include x1, x2, and x3. Another subset would be x1 and x2. Another one would be x2 and x3. Another one, x1 and x3. Another one would be just x1, or just x2, or just x3. So we can have 1, 2, 3, 4, 7 possibilities. There are 7 possible subsets of this 3 independent variables. When we have 3 independent variables, there are 7 possible subsets. Okay, so we can try each of the 7 models because each one is a different model. We can try each of the 7 models and see which one results in a higher accuracy in of the model on the test set, and we just pick the most accurate model, and that would be our model. So it could be just x1 and x2, or it could be just x1, x2, and x3. We don't know. Okay. But let's say we have 10 independent variables, 10 potential predictors, x1 to x10. So we have x1 to x10, and we want to try all the subsets. Try all the subsets and then select the best one. Okay. So how many subsets do we have here? How many potential models do we have? It's combinatorial analytics. Then we have 10 potential predictors. So I can give you a hint. Each variable can be in the model or not be in the model. So for each variable, so you see, for example, one model can be this, not variable, not the first one, but the second one, but not the other. Not the first, not the second, into x3 and x4. And another one would include x1, x2, and up to x10, all of them. So there are very many different models, right? But each variable can be in the model and not be in the model. So there are 2 possibilities, 2. So total number of combinations, total number of possibilities will be 2 times 2 times 2. 2, 2, 10. So there are 2 to 10 possibilities, except one of the possibilities, one of the models is not acceptable. Which one? The one without any variable. So we should have at least one variable in the model. So we have 2 to 10 minus 1 combinations or subsets, right? How much is that? It's 1023. So we have to try out 1023 models and see which one results in has the highest accuracy on the test. It's gonna take a long time. But we can automate it. We can write a program, an algorithm that can just try out all the models, and then we select the one with the highest accuracy. But in real life, we usually have way more than 10 potential predictors. In real life, we have like maybe 100 predictors, 100 independent variables that can become predictors. And that means in real life, we may have 2 to 100 minus 1 possible models to test. 2 to 100 minus 1 subsets, right? And how big is this number? Do you have any idea? So I can give you some idea. 2 to 10 is a little bit more than 1,000. 2 to 20 is a little bit more than 1,000,000. 2 to 30 is a little bit more than 1 billion. 2 to 40 is a little bit more than 1 trillion. 250 is a little bit more than 1 quadrillion. So 2 to 100 is more than million, trillion models. So even if you do it automatically, and even if each model takes 1/1,000,000th of a second to build and test on the test data set. So, each model should be built, should be estimated, and should be tested on the test data set. And that means should be tested on all the data points in the test data set, and you should calculate the errors, form the confusion matrix, and everything for each model. And let's say each model takes 1/1,000,000th of a second. You have a supercomputer or something. So this means if you want to try all 1,000,000 trillion models, it's going to take years, actually thousands of years to test all of them. So probably this is not the best approach. So trying all subsets is going to take a lifetime. There is also another problem. When we have too many variables and when we try all of them, some subset can, just by accident, can result in a very high accuracy on the test set, just because of noise and just randomly. One subset can result in a very high accuracy, because when we are trying many subsets, just randomly one of them will perform very well. And that doesn't mean it is a good model. It's just a lucky model. And we are actually overfitting our model to the test data set. We are overfitting our selection to the test data set. And even though the model would perform good on the test data set, would have high accuracy on the test data set that we have, it would not perform as well on another data set, a second test data set. So we are again overfitting, but it's just in another way, in variable selection, in selecting the variables. So this is not a very good practice. Actually, the best way is to consider some theories and some meanings of the variables, consider the meanings of the variables and the actual relationships between the variables based on intuition, and then decide what variable to include in the model and what variable not to include in the model, what to include and what to exclude. So Essentially, we are considering our expectations when we include the variables, right? And so in hierarchical selection, we add the variables based on intuition, and we see how good the new model does, and based on that, we decide to keep the variable or not. And then we add another variable, and then we add another variable. So for this, we need to have some understanding of the context, some understanding of the data, and we should have some strong theories backing our decisions. So this is very good. This is a very good method if we have theories. Go ahead. Oh, keep adding variables. So adding grades. We never did that before. Have we done this? I didn't. I don't remember showing you hierarchy.
I don't know.
No. So first of all these methods can be applied to multiple linear regression or logistic regression. You can apply it to both of them. But I have not shown you a hierarchical selection so far. Okay. So, and we can judge the model based on R squared or just accuracy of the model on the test set. Another method is just to add the variables based on how much they increase R squared. So what we do is that essentially we try out adding each variable, each of the potential variables. So we start with no variable. In forward stepwise regression, we start with no variable. We try adding each potential variable, each potential predictor to the model, and we see which one results in the highest increase in R squared. And then the one that increases the R squared the most will be added to the model, will be kept in the model. Then we go to the next spot. So we want to add another variable. What we do is that we just try out every variable that is remaining, every one of the remaining variables, one by one, and see which one increases R squared the most. And we add that one. And at some point, we see no increase in R squared by any of the candidate variables. So any of the variables that we add to the model will increase R squared substantially. And that means we have our model. We don't need to add any more variables. So this approach has a serious problem. And the problem is that when you add variables one by one, and you are not considering the interdependencies between the variables. So you're comparing the variables in isolation. But sometimes the variables have interdependencies, and the effects can be different when the other variables are present in the model. So you want to consider the effect of the variables when other variables also are present. Okay. So now we get to the last method, which is the best. Backward stepwise selection. So in this method, you start with all the variables. At the beginning, you start with all the variables, you include all of them in the model. Then you drop one variable at a time. You drop one variable and try the model without that variable and calculate R squared, and then drop another variable and try the model without that variable and and calculate R squared and see dropping which variable results in the least reduction in R squared. That means you find the model with the maximum R squared that has one less variable. Okay. So the same number of variables, maximum R squared. So when you find that, we remove that variable. We know that that variable has the least effect on R squared. And and then we just repeat that. We just go and find the next variable to remove, and the next, and the next. And at some point, removing any variable will result in significant reduction in R squared. And at that point, we know that we should not remove any more variables. And we have a good model. So I should mention that we are making decisions based on R squared. And of course, R squared means just the fit of the data to the training, the fit of the model to the training data set. And we prefer to have a generalizable relationship. So we should just keep an eye on the accuracy of the model on the test data set. And when we use backward stepwise selection, we are including all the variables in the model. We are including most of the variables in the model when we are testing the variables. We are testing the effects of the variables. And that means we are considering the interdependencies between the variables. So let me show you the algorithm that we use to perform backward stepwise selection. First, we start with all the predictors, all the potential predictors in the model. And we find the R squared. We remove the non-significant variables. We run the model, we find the significant and non-significant variables. We remove the non-significant variables from the model. Then we remove one variable at a time. We remove each of the variables and run the model for each removal. Essentially, we run the model k times, removing k variables, right? So we run the model k times, each time with k minus 1 variables, right? And we compare the R squared across different models. The model with the least reduction in R squared is the best, or the model with the highest R squared. Okay, and then we repeat. We go and we go back and we try to remove another variable. We want to remove as many variables as possible without reducing R squared significantly. And at some point, we cannot remove any more variable without a significant reduction in R squared. And that's the point that we have the best model. So I should mention that overfitting is still a danger. It still can happen because our criterion is R squared. We are trying to minimize this possibility. And underfitting is also a danger. So we have low R squared. We should avoid that. And the decisions are subjective, and you should always consider reasoning and intuition and the meaning of the variables. So you should always keep an eye on the accuracy of the model on the test data set. So what we do is that we usually use R squared for linear regression, and we use prediction accuracy for logistic regression. So as a reminder, we want to have the model as simple as possible with as few variables as possible, but at the same time, it has with the highest R square as possible. So let's talk about an example, the packages data set. So when we see the complete data set, I think we have like 14 variables. So the dependent variable is average hours per driver. We start with all the other variables as predictors, except the fuel cost, because it doesn't make sense to include that. So consider intuition in building the model. So, and we run the model. This is the result with all the potential predictors in the model. Okay, this is the result. So, what do you see here? What should we do now? What?
So removing variables.
Removing which variable?
Which ones?
What? Least effect on R squared. So at this point, we have just one R squared. It is 9963.
You want to take out your stars.
Exactly. We should first remove the non-significant variables. That's correct. So first, we should remove the non-significant variables and keep the significant ones. So we have these variables are not significant, and these variables are significant. So we keep the significant ones and we remove the non-significant ones. Okay. What's your name?
Chase.
Chase. Oh, I remember you. You have answered all the questions, right? No?
Yeah,
This was your first time?
I have it for.
Oh, okay. So, good. So, we keep the significant variables and we run the model again with the significant variables. Of course, all the variables are significant now. And so, the first iteration, for the first iteration, what we do is that we run the model 10 times. We have 10 remaining variables. We run the model 10 times, each time with 9 variables. Each time we drop one of the variables. And we compare the R squared values. So we have 10 variables, we run the model 10 times, and we see the result in R squared each time. So the original model with 10 variables is up here. Its R squared is 99.9962. When we remove packages delivered, the resulting R squared will be slightly smaller. The difference is here. It is the amount of reduction in R squared when we remove that variable. We remove the other variable, this is this. So we have the R squared reductions for all the variable removals. Okay. Now, which variable should I remove? Which variable is the best variable to be removed at this stage? Drivers working. It has 0.111 reduction in R squared. Why? So it has the largest reduction in R squared. So when we remove this variable, we lose the most. Weather conditions. Why? Has the least effect on R squared. Exactly. Thank you. So weather conditions is the best candidate because it results in the least reduction in R squared. So we should remove weather conditions. And we lose the least, essentially. So now, so the next step would be what? the next step would be just run the model without weather conditions. We already did that. So now you should just try 8 different models, 9 different models, each with 8 variables. Just remove another variable.
The goal is just get one variable.
No. The goal is to have the minimum number of variables and maximum R squared.
So why won't you just use the ones that all significant?
Oh, that because the significance levels change when we remove the variables. Sometimes something that is not significant may become significant actually.
Like for this one, like you said you wanted to remove weather conditions, right?
Yep.
And that's the only one that wants.
It happened to it. It is usually the case. It is usually the case, but it is not always the case. Sometimes we have some effects like suppression or spurious relationships. And in such cases, actually, you may, when you drop a variable, you may have a larger effect on another variable.
Oh, okay. So you got rid of it just because you was like, when it said 0, it's doing nothing.
What?
Like when
The difference is 0?
yeah.
So it is not actually 0. When you drop a variable, R squared decreases, no matter what. R squared definitely decreases, but the decrease is so small that you cannot see that in decimal places. So the next step is that you should choose the next variable to drop, and you should choose the next variable to drop, or decide that no other variable should be dropped. Any other variable, if dropped, it's gonna reduce R squared significantly. Okay, so you should do that at home. This is your exercise. You should just do the next step and let me know what's the model with 8 variables. Okay, good.
So how do you know where to stop dropping there?
So at some point, you see that if you drop any of the variables, R squared drops significantly. R squared decreases significantly. So there is no variable that you can drop without losing a lot.
You have like a measure of what technically is significant.
It's just subjective. It's just subjective, but usually it is easy to detect. It is not. So you can tell. So if R squared drops from 96 to like 43, that's significant dropping. But if it goes from 96 to 95, it's not. Go ahead.
Could you go back to the other, like the slide column? Yeah, this one. So would you want to have resulting R squared descending order?
It will be descending, definitely. So each time that, here,
Yeah, like right here, it's just like, I don't know.
oh yeah, you can do that. When you
Yeah,
sort
would
it,
that make it like the most
yeah, you can do that.
easiest way to tell, like, for what he was asking?
The next variable, what the next variable will be?
Yeah.
No. So when you drop this variable, the model changes. And then each time you should just try out all the variables again. Because you may say that, okay, next variable that should be dropped is percentage damaged.
Yeah.
Because it has like this. It is not like that.
Alright.
So when you drop the percentage damage, this is the reduction. After you drop, you don't have the weather condition in the equation.
Doesn't that also?
It is more
Alright,
likely.
never mind.
It is more likely that this is the next candidate. This is the next variable that should be removed. But sometimes it is not, because this reduction happened in the presence of weather conditions.
Okay.
But
Yeah.
when after we remove the weather conditions and the weather conditions is out of the picture, we are going to run the model again. We are going to remove this one, and we will observe different reductions for different variables. So do the next rounds at home and let me know what's going to be the next variable and the next variable. So now I'm gonna do an example in R and show you how to select a variable in R. So just to make things simple, just to make the example easy, I'm gonna just try to predict average hours per driver as a dependent variable using three variables: weather conditions and percentage oversized and holiday. Let's imagine that these are the only three variables in the data set. Okay, so let's see how we do backward selection. We go to R. Change the working directory. And read the packages.csv. It has these columns, but we don't care about all of them. We just include three of them: percentage oversized, weather conditions, and holiday. We run the model with the three variables.
Well, you can't say.
Oh,
Not the HTML code output.
no, it is actually there.
It's like, it doesn't have an HTML signal, so.
So you read the packages.csv using this command, and then you run this model with all the three variables: percentage oversized, weather conditions, holiday. Okay. So these are all the three variables that we have in the data set. Just imagine this is the case. R squared is 46. 46. It's R squared. So for backward stepwise selection, so first of all the variables are significant. All the variables are significant. So step 0 is done. Then I'm gonna try removing the first variable, percentage of oversized, and see what's the resulting R squared. R squared becomes 0.14, a significant drop, obviously. Try removing the other variable, weather conditions. R squared becomes 0.22, substantial drop, obviously. Let's try removing the other variable, holiday. R squared becomes 0.45. Okay, it's very close to the original model, 0.46. So not significant reduction. So I'm gonna remove that. So that means we are left with two variables, percentage of oversized and weather conditions. What is the next step? We are gonna see if we can remove any of these two variables. So I'm gonna remove percentage of oversized and run the model only with weather conditions. R squared dropped significantly, 0.13. No, actually 0.14, still significantly. And I dropped the other variable, so we have just percentage of oversized and run the model. R squared is 0.21 or 0.22. Still a significant drop. So that means what? That means we cannot remove any of the remaining variables. The model, the ideal model, the optimal model is this. Not the ideal, the optimal model is this. Average hours per driver versus percentage of oversize and weather conditions. So we have these two variables as the best variables among the three variables that we had. Okay. So it was a very simple example. So now let's try with all the variables and do the example that I explained to you. Just include all the variables and try dropping each variable at a time. So, good. I'm here to answer any question. By the way, thank you for the feedback and on the survey. So I did your feedbacks. So the comments were mostly about speed, change the speed of drivers. So ask them to slow down. So I think they want to, right? Like teaching fast, slow. Okay. That's good. And another comment was that we should practice together. Fast, I should get you to practice in the class. So, practice on. And the other comment was about answers to the assignments. So, you're gonna just answer the assignments, the questions of the assignments, especially before the final exam. Because I want to give you all the material before the final exam. So you won't get the final exam. So you have to answer all the questions with assignments. Good. So now you just try backwards stepwise regression. By the way, backward stepwise regression or backward stepwise selection, backward selection, they're all the same.
Should we have pictures? Or just?
Oh, you should have pictures. Okay. You should have TV, standards. So I put an example. Right. I'm seeing a discussion. What is the last discussion that I see? Let's go to the Sure. Any question?
I removed the first I removed
Yeah.
year of the year.
So why? Okay, so you know that you should first run the regression with all the variables, and when you do that, you get the coefficients, and right off the bat, you see that year, weekend, and holiday are not significant. So you can write all the three at the first step. And then you should try the others one by one.
Yeah, that's what the other ones you have to do one by one.
Yes, you have to do one by one. And most likely it's going to be better conditions. The next one will be better conditions.
Yeah.
And then I want you to tell me what's the next. What is the one that you drop after weather conditions, if any? So please do the example at home after the class. And yeah, so practice backward stepwise regression at home. So now let's talk about outliers. So it's a quick PowerPoint. I'm gonna just show you how to handle the outliers, and we have time for that. So outliers are the cases that are significantly different from the other cases, are actually outliers essentially. So they are not aligned with the other observations that you have, and they are like abnormalities. And these cases, these observations do not make your model, your estimation better, because they are special cases and you want to try to predict the typical cases. The goal is to predict the typical cases. So they are going to sway you away from predicting the typical cases correctly. So for example, let's say we have these data points. The regression line would be something like this. And but if we have this outlier here, we have this data point that is far from the others. Since it is far from them, it is far from the average, and its error, or its error squared, has a large effect on the coefficients, and it can just change your model, change your estimated coefficients, which is not fair. So just one observation is changing the coefficients in your model. It's not good. It's not what you want. So what happens is that we want to deal with this outlier somehow. So we have an example, the taxi driver example, the taxi data set example. We're going to talk about that later. But so the example is about fare versus distance. So generally, when we go longer distances, the fare should be higher. Naturally, that's what we expect. So if we see anything unusual, probably it is an outlier. So how can we handle outliers? First approach is to ignore them. Just keep them in the model as if they are not outliers. As I explained before, they will affect your estimations, and they bias your estimated your estimations. So another approach is to trim the outliers. That means just remove the outliers from the model, exclude them from the model. To trim the outliers, you should specify what are the outliers. There are two main methods to specify the outliers. One is IQR, and the other one is percentiles. There is also a third method. The third method is just visual observation. So you should just look at the scatter plot and see which ones are outliers. So that also is a method. But the systematic method would be percentiles or IQR. The other approach to deal with outliers is Winsorizing. So in Winsorizing, we are going to specify the upper bound and lower bound, like what we did for trimming. So we can use IQR or percentiles. But here, we do not exclude the outliers. We move them inside the acceptable boundaries. We move them. And then we can just run the model like regular. And we use Winsorizing when we have very few observations, we don't have a large data set, and we are short of degrees of freedom. So we want to keep as many observations as possible. In those cases, we try not to lose any observation. So we just move the observations around to just not to bias our estimations. So the first method was ignoring, and that's not the ideal approach, but sometimes we may not care much, especially when we have too many outliers here and there. So we may think that probably outliers are actually an important part of our data set, an important part of our model, so we should consider them. Sometimes we decide to keep them. The second method to handle outliers is trimming. We should specify the upper bound and a lower bound for each of the variables, independent and dependent. And we remove the data points that are outside those boundaries, upper bound and lower bound. How do we specify the lower bound and the upper bound? We can use percentiles, or we can use IQR. So with IQR, what we do is that we just, the lower bound would be the first quartile minus 1.5 times the difference between the first and the third quartiles. So the middle quartile. And the middle half of the data. We want to see how wide is the middle half of the data. The upper bound would be the third quartile plus 1.5 times the difference between the third and the first quartile. So you don't need to just memorize these formulas or even understand them. You can just use the formulas from the PowerPoints. Okay. So don't worry about that. But using percentile is much easier. We just take the top 1% and lowest bottom 1%. So we just remove the top 1% and the bottom 1% from the data. So sometimes we may use other percentile measures, but 1% is the normal conventional approach. But if when you use percentile, you lose a large portion of data, that means there is a problem. Maybe your data is so skewed that you have a lot of data in the extremes. In those cases, you should not use just percentile. You should use the IQR method. So that's about it. So now what winsorizing? When we have winsorizing, again, we have to specify the upper bound and the lower bound when we want to use winsorizing. But instead of excluding those data points outside the boundaries, outside that, we should move them to inside. We should move them to have them inside the boundaries. And again, we can just use IQR or percentile to move to specify the outliers and reassign the outliers new values. So which method is the best? Ignoring, trimming, or winsorizing? Depends on the situation. So usually we should use just intuition to decide, and we should see how serious the outliers, how serious of the problem the outliers cause, and we should test the errors before and after removing the outliers. We should test the errors and test the accuracy of the model on the test set before and after removing the outliers. And the ultimate criterion for us is the accuracy of the model on the test set. So if removing the outliers improves the accuracy of the model on the test set, that means it's good. The model became more generalizable. But if not, probably it's not a good idea to remove the outliers. And you should just decide based on the accuracy on the test set. But generally, trimming with percentile would be good enough. Unless you don't have enough data points, in those cases, if you don't have enough data points, you should just use winsorizing. But percentile would be enough. And so you use percentile by default unless a large portion of data will be excluded if you use percentile. If that's the case, you use IQR. And you use trimming normally, unless you don't have enough data points, in which case you use winsorizing. Okay. So let's go to R and see what we So here, first, let's change the working directory. First, we have to change the working directory. And this is the working directory that we did the taxi dataset. It's a very large dataset, so it's about 500,000 data points. Plot the x versus square versus distance. See what's the result. Takes time because it is a large data set.
forever.
Sound right? It should show this message.
Oh, no.
So move something like this stuff for a month.
Yes.
It's probably because of how you have it zoomed around.
Oh, okay. Oh, now it's doing something.
It may just not render. It's a lot of dots.
Maybe I should close it. Should not use the taxi data set. It's not good. The margins are too large. This message.
Is that what it says? The margins around the figure are too large for it to display.
Could you just see the scatter plot? Any one of you? Just one? You could see the whoever could see the scatter plot. Put it on it. Just one, just two. Okay. My computer is too slow apparently. I don't know if I should wait or
No, um, yeah, if you have the, yeah, it won't do anything. The console is ready for next input,
yeah, you're right.
so it's not processing. Your
It's not
computer just
processing.
cannot display it. It's too much data.
Yeah. So let's see. Actually, we don't need the figure anyway. We can just go to the code. So how many data points do we have? Length of one of the columns, any column. So the number of data points will be number of data points. Something is wrong with this computer. Is so the next step is that we take we split the data. Since taxi is just the number of trips, the observations are trips, it is not a time series, and that means we should take a random sample, select a random sample of the data. 70% of the data we take randomly. We select 70% of the data for training, and we use the rest for testing. So train equals sample. This command, we do the job, and then the rest would be in test. And just to get the training data set and the test data set, we should just apply the indices that we found to the data set. So we have the data frame here. D of the train would be the train, and D of test would be the test. So, and then we are gonna just we can just plot the training data set. That's fine. We can make the scatter plot for just the training data set to see the outliers that we have in the training data set, because they are the ones that matter. Remember, we excluded the outliers to make a better estimation, to improve our estimation. So the outliers that are in the training set are the ones that can sway our estimations, can affect our estimations, can bias our estimations, right? So that's what matters. So first we run the model, just fair versus distance, without handling the outliers. So this is the first method. Just ignore the outliers. Run the model without doing anything about the outliers, and see what's the result. And then you run the model again using the. So you want to use the second method, that is trimming. So you want to find the upper bound and the lower bound to specify the range, the acceptable range for your data, and you specify the upper bound and the lower bound for fair, and we're using the IQR method here. These are the formulas for IQR. And then you have the this formula here to use to exclude the data points that are above and beyond the bounds. So they are above the lower bound, or so you keep the points that are above the lower bound and that below the upper bound. So you see, I'm gonna just find the data points that are between the lower bound and the upper bound, and I get that data from the training data set, put that in T. So I'm trimming the outliers here. And then I run the model again using the trimmed training data set. Using the trimmed training data set. Okay, so let's continue next week, because it's not working. It's not showing anything. I cannot run any code. So thank you.